Coming. Hopefully everybody got to go see the car, drive around a little bit. Pretty awesome. We're pretty excited. Glad to have everybody here. We're going to run through a quick little presentation that we gave the president of the school a few weeks ago. Kind of just details what we think makes us kind of the next level Formula team.
So while we do go to competition, the other 99% of the time we're not at competition doing those specific events. So we thought we'd highlight the things that we spend most time doing. My name is Brian Ginther. I'm the project manager of the team.
Tyler Peterson, the chief engineer.
Right now we'll just go through the whole scheme. I want a little bit more light now. So right now we'll go through the whole team. Just quick introductions to get an idea of how many people we have actually involved with making that car you saw drive this morning. I don't care where we start.
Start with Peter.
Okay, down there.
My name is Kevin Alvarino.
My name is Taylor Bridges, Composite Manufacturing.
I'm Connor Kehoe, Fabrication Group Leader.
I'm Kyle Abbott. I'm the brake system engineer. Phil Vars. I'm the lead powertrain engineer. Tim Moran. I'm the lead chassis and suspension engineer. Chris Kotorski. I'm in the powertrain group.
I'm Nicole General. I'm in the powertrain group. I'm Shelby Abram. I'm in the composites group.
I'm Megan Kujenski. I'm in the fabrication group.
I'm Christina Kushko, and I'm in composites.
I'm Matt Craven, and I'm in the fabrication group.
I'm Andrew Dodd, I'm this year's CNC group leader.
I'm Aaron Lee, the lead vehicle analysis. I'm Kevin Ferraro. I'm the lead aerodynamics.
I'm the electronics work.
I'm Andrew Durhammer, Composites Group.
Patrick Burke, fabrication group.
Dylan Bruce, fabrication group.
Joe Malowitz, composites group.
Adam Stinkheimer, composites group. Jake Swanson, composites group.
Sam Young, CNC. Over here, CNC group.
Tim Rice, fabrication group. Logan Ford, fabrication group.
Thomas Cannon, fabrication group.
Rattler, fabrication group. John Washington, fabrication group.
Alex Hebert, fabrication group.
Robert Boyak, fabrication group. Jeremy Adams, powertrain group. And Unity Electronics.
So that's about, overall we have about 40 people on the team. Of that, about 15 brand new members, 15 more returning members, and then about 10 or 12 group leaders who are responsible for designing the car. So it's quite a big team we have, and basically we use everyone's abilities the whole year to put together the car. So when you look at the team as a whole, we're really a very small company. Everything that an engineering company does to create a product to sell to whoever, we do the exact same thing. So we do the same sort of development process. We have the same design considerations as far as designing to be able to manufacture it or designing for a little bit more high performance of a part. And at that same time, we're doing all sorts of engineering trade-offs between maintenance and cost, everything that a normal company thinks about. Also, we do some, not hard engineering, but some of the soft skills. We're doing cost analysis, budgeting, as well as scheduling and timeline and marketing.
So for 2012, we had some pretty big changes. We always had run a 4-cylinder engine, same one for the most part. We actually switched to a single cylinder, went to a full composite monocoque chassis. First time we had wings on the car. It was a big jump for us. It was a lot of work. We learned a ton. That sort of launched us into this year where we decided we'd learn a little more and wear ourselves out again and try even harder.
This past year, 2012, we got 5th place overall in Formula SAE Germany, winning the final endurance event and getting 2nd place in fuel efficiency. So
it's a pretty prestigious event. There's about 10 competitions worldwide that are recognized. Every team that had won every competition, except for one team, was at that competition. So that's sort of the all-star game, as we like to think of it. So winning endurance there was pretty awesome. So we got some highlights for the 2013 car. One of the biggest changes is we've turbocharged the engine. It's taken a lot of resources, but it's proven to be really helpful. We've really stepped up our game when it comes to the FEA and physical testing. We don't just make guesses with this. There's a lot of very tedious calculations, a lot of planning to try to make the parts, and then testing parts to make sure that they do what we think they will based on our calculations.
So the FEA is a structural analysis, pretty much simulating the part and then applying whatever loads that we've calculated and seeing how strong it is by either the stress that's developing in the part or the deflection. With a race car, we really are concerned about how stiff everything is to be able to properly tune the car.
Yeah, and a The reason we can make those steps this year is we got some new software sponsored from Siemens. It's the DMAP software. If anybody's familiar with that, we actually got about a $3.1 million donation. So that was really big for us. We're obviously a small group, but being able to have the computing power to do some more design work was really important. We've also moved to having a lot more bonded joints. We proof load all those. So we're not just building parts and throwing them on the car and crossing our fingers. We actually go down to the lab, use the equipment. We're familiar with it, know how to use it, make sure everything will take all the loads we calculated.
We've also implemented a pretty structured design review process. It's the same design review process that every aerospace NASA uses to qualify and make sure that their designs are going to meet whatever specifications that they need to meet. We do design reviews at specific stages within the project, starting with a preliminary design review, where you're talking about your basically beginning calculations, how you're analyzing the structure, where all your loads are coming from, what your safety factors are, pretty much your beginning ideas, and kind of a good chance for other team members to offer early input. Pretty much correct any early errors that you made, any wrong assumptions, but basically getting getting the team aware of where you are now and where you're going. After a few weeks, you can move on. We would do the critical design review. That is pretty much you've done all your analysis. You're ready to present all the results of the analysis that you've run. You're pretty much ready to make prints. You're just double checking with everyone, make sure that you've caught all the supplier issues that you might have run into. Manufacturing is aware of all the challenges that are coming up. We have all the tooling, all the fixtures that we need, etc.
And the bottom line what that comes down to is we're able to build a more refined car. We come together, nothing's the first time you've seen it when someone's bolting it on a car. Everything fits, comes together, car works together better as a whole.
And this overall, each assembly on the car has been refined, lightened, stiffened, and we've done that throughout the whole car. We're going to go through a few of the highlights that we've done. This year we've obviously turbocharged the engine. Real companies are doing this as well to increase fuel efficiency. The CAFE standards that are implemented by government specify a minimum fuel economy for fleet-wide cars. And we're trying to work to the same goals with the points emphasis when we go to competition. If we burn more fuel, we get fewer points. So it's the same sort of development process that Ford has been going through with their EcoBoost line of engines. It's a small displacement turbocharged engine. Also, we've done a lot of simulation work with the engine. The powertrain with the turbocharger, there's a lot of nuances with the geometry of the parts going into the turbo and coming out. And if you can simulate the whole thermal cycle of the engine before you make any parts, you can tweak basically how the engine is going to perform throughout the whole range of loads that we're going to see. These two plots are the efficiency of the turbo, and basically if the line that is being plotted kind of follows that kind of the red line, that's going to be where you're most efficient, and we basically tweak all the parts and simulate them to arrive at a final product that we're going to actually make, and hopefully it'll work right the first time. So we don't have to waste time fabricating and manufacturing a bunch of different iterations only to be basically waste all that time, the material, and money. We can kind of do that all virtually.
So here's VMAP. This is the software we were talking about. It's a Nastran-based FEA. And like Brian said, basically we import geometries that we draw on the computer. We're able to input our boundary conditions and tell it what kind of materials we have, and it simulates what we're going to see. The biggest thing we've used that for this year was the chassis, which is that full carbon fiber monocoque. Tim spent a lot of time working on that, and through this more powerful software compared to what we used before, we were able to refine the chassis, get a lot better idea of what it's doing, and get more accurate results. And also pictured is the steering support, and then our main engine mounting system. So real companies have to meet safety requirements. You can see the bottom right-hand picture is a picture of a Formula 1 car being crash impact tested. In our rule book, we have to deal with the same sort of requirements. We have to have a crash structure on the front of the car that can absorb a certain amount of energy. So we've designed the nose cone, while it's very functional in holding the front wing, is also an impact structure to absorb energy in the very unlikely event of a crash. So we have to go out to Michigan and run this physical test to collect the data
and show that our design has met the specifications laid out in the rules.
That's something that not a lot of teams are doing, which is part of the reason we're so excited to do it. It takes a lot of work. It's a hard thing to calculate, so you end up doing some iterative testing. And there's probably only maybe a dozen teams in the world right now from the Formula team circuit that are doing this. Most people literally just have a block of foam or a block of balsa wood on the front of their car. So we're stepping a little beyond that design-wise.
We're one of the few teams that design and engineer our entire braking system for our own car, custom made. A lot of teams buy their own calipers, rotors from motorcycles, ATVs, and fit them to our car. We like to be able to optimize each component based on how much energy is in our car, and then we can design a system to meet those requirements. In order to enhance that design, this year Kyle made a brake dynamometer to basically measure the brake pad friction coefficients and kind of characterizing how the brake pad performs over a range of different temperatures, trying to decide what kind of thermal mass that we need to reach to keep that pad at the optimal temperature.
Yeah, we spent a lot of time on fastener design this year. We've talked about all the FEA we're doing, all the computer simulation, but that only goes so far. And what we found is we're designing some of these brackets. We have about, 24 of them on the car, and basically each one of these holds on an arm. And we were running all these calculations, and the computer was saying they're blowing up, but we can also go back and do math by hand, and that says they're okay. So we kind of get to this conundrum of, do we believe they're really expensive fancy software, or do we believe the hand couch people have been using for 60 years? And the best way for us to figure that out was to just do some actual testing. So we built some parts and tested them to failure. We found some pretty useful papers from NASA, and those ended up pretty much validating what we expected, which was the hand couch were okay. So again, we're going beyond just the normal, a lot of people would tend to just throw all these parts into FEA, look at the colors, design from there, and go for it. But we're really getting to the point where we got to refine everything. You got to double check all your numbers, and we really got to make sure that everything's going to work like we expect. We can't afford to make any big assumptions like that.
And with our pretty aggressive weight goals, we really can't have any extra mass on the car. So.
Yeah, if anybody didn't know, the car only weighs 335 pounds. This is the second year we've had a pretty lightweight car. Traditionally, we've been up more towards the 450-pound range, so pulling all that weight out of the car is a big part of it is a single-cylinder engine, but a lot of it's just being able to reduce the mass of the structural parts themselves.
So these are just some NASA kind of recommendations. Like we were talking about before, we had a pretty good idea of what needed to be covered in each stage of the design review, but this kind of just really showed that real companies and real NASA, whenever they fly any sort of space probe, the shuttle, they have to go through very specific and rigorous design reviews to make sure that all those design specifications have been met.
So for our 2013 season, which is just kicking off, we'll be heading to Formula SAE Michigan, which we go to every year. It's our first competition. We'll be leaving for that on Tuesday. There's usually 120 teams from around the world. Very competitive. We have gotten second many, many times, and we're hoping to bring home that big #1 this year. So we'll give it our best. I think we have the car for it, we have the team for it. And then later on this year, we'll be going to Formula Student Germany. 5 of us are leaving the end of July. We'll go and test with a German school that we're friends with, stay over there for a week, and go to competition. And as Brian was saying earlier, we did really well last year. We didn't finish as well as we wanted in all the events, but we did do very well. And if we can bring up our performance in all of the events, we stand very well to actually do better than 5th, because we've only ever gotten 5th or not finished, which is kind of disappointing. So pretty much anything lower than 5th would be good at this point.
All right, so I think that's it. Can we have some lights a little bit? That's really what we wanted to cover pretty quickly. Does anyone have any questions or anything at all? Right here?
Can you tell me the criteria that you're evaluated on when you go to the competition?
Sure. When we go to competition, there's basically 7 events. There's 3 static events where we're just presenting to judges, and then 3 driving events. The 3 static events are cost, presentation, and then engineering design. Cost event is kind of simulating if you were to mass produce these cars, how much would the car be, basically an MSRP for the car. How much would it cost to make each part, and then assemble each part, and put each assembly on the car. Presentation is a sales presentation to a group of simulated investors. If you were to take this car and make a company that was making it and selling it to the customers, you would need some startup money from basically venture capitalists. And you would need to basically present a business plan to them and show that you have a market and a demand for your product. Engineering design is the most prestigious event at competition. It's actually it's an engineering design competition, and this is the engineering design event. So we basically present our car and all the engineering decisions that we made, all the design process that we made, and present it to a panel of judges who are typically industry experts from aerospace, motorsports, engineers who are experts in their field, and we have to show that we understand the engineering trade-offs that we made, the engineering decisions that we made, and how we know that the car is actually physically performing to what we designed it to be. Kind of just closing the design loop to analyzing something, predicting its performance, and then measuring its actual performance and showing that all your design is working out properly. The 4 driving events are skid pad, which is a figure 8 track. We just do 2 right-hand loops and then 2 left-hand loops. That's testing the cornering ability of the car. The car gets in a steady state cornering, and basically the better cars with a better suspension can maintain a higher lateral acceleration for the circle. It's a pretty standard test that kind of removes a lot of the driver input from the car. Just because it's a circle, you can't go.
Hey. Someone's worked very hard driving that circle.
But much more than an autocross event where there's lots of uncertainties, basically. And then the 2 final driving events are autocross, which is a single lap of a road-style course. Each driver has 2 chances at the best time, and we have 2 drivers. The endurance event is a 22-kilometer event of basically it's about 20 laps of the same autocross course with a driver change in the middle.
But with multiple cars out on the track. We're not necessarily racing wheel to wheel, but there are multiple cars and there's passing, so it's a little more fun for everybody to watch.
Right. So they try to keep everything safe and controlled, so it's not a NASCAR style first, second, third. It's time-based with cone penalties and things like that.
And then we also have an acceleration run,
Right.
75 meter, basically drag race, see how quick you can get. We're usually 0 to 60 times, somewhere around 4 seconds, which is really, really quick. So people always ask how fast the car is. It goes about 60. You'll notice it's got big wings, it's super light, but we do get there in a hurry. So.
Can you explain your decision to go from 4 cylinders to 1 and what you hope to gain with that?
Basically just came down to mass. We tried to simplify the car, bring everything in. 4-cylinder engine wet, I believe it weighs like 110 pounds, something around there. What's a single like?
About 70 pounds.
Yeah.
So
it's really rewarding to know that you want to take the engine out and unbolting it and then picking it up and setting it on a table. Added benefit.
we wrote a MATLAB simulation kind of comparing different types of cars, and basically we put in like a 4-cylinder car with no aero that can accelerate really fast but can't corner very hard. And we also put in the parameters for our type of car, which is very lightweight, with an aero package, but with a smaller engine that can't accelerate fast but maintain a higher lateral load. And through all the math, through each type of turn, accelerating, decelerating, like the slalom, the math basically showed that our car would earn more points at competition. And that drove our vehicle level vision, and then we worked from there to see what kind of aero loads that we want, what kind of power we want, etc.
Did you give up anything in terms of power?
Yeah, we gave up some in power, not much in torque. Last year was a lot of work just to get the engine going. This year we looked at the simulation again, and it did tell us that we could have something to gain from having more power, which is what drove us to run the turbocharger. It's a very fine balance, though, when it comes to balancing how much the turbocharging system can weigh and what we would get back from that power.
Switching from the 4-cylinder to the single cylinder, we do cut, like from 2 years ago to last year, we did cut about half the horsepower, but the equation was a lot more complicated than that. There's a lot of other factors that make the car faster than just straight
Did your
horsepower.
fuel mixture stay the same? From the 4 to the 4-cylinder to the 1-cylinder?
For the most part, yeah. Like it's only 1 cylinder, so there's a little bit more tweaking.
One of the biggest tricky things with a single cylinder that sometimes catches people off guard is the 4-cylinder. You got 4 chances to get something right. Pretty easy to start, pretty reliable. A single's a little more picky, because if you don't get it right on that single cylinder, you don't have an engine. So.
Is there any other
Anybody
questions?
else?
You guys should talk a little bit about your roles on the team, like, you're pretty much running the business, so it's kind of cool to explain.
Sure. Like I was kind of explaining at the beginning, we're basically a small engineering group, and every role that you see in a corporate company is kind of mirrored with us. So there's engineers, draftsmen, manufacturing people, but up towards the top there's executives, CTOs and CFOs. I would be more of a administrative CEO type person. I'm responsible for the money, the budget, timeline, making sure that we have all the supplies we need, working with school administration to have all our paperwork in, and as well as just dealing with any issues that come up that prevent engineers from doing their job or accomplishing what they want. Basically, I try to take all these issues that come up for designers and try to remove those barriers so they can do what they want.
So basically, Jack gets to spend all of our money, which is kind of nice. I, on the other hand, take care of all the technical things. The way I like to think of it is Jack takes care of a lot of the external details, so the budget and everything. I get to deal with all the internal things with the team. So everything from those first design meetings when we're deciding what we're going to do, what we want to shoot for, all the way up to helping people get things manufactured and making sure the car comes together.
I try to put myself in a role so that people only need to worry about race car things and making the car fast. They don't need to worry about getting money. They don't need to worry about where their shipment is, where their parts are, things like that. So they can only focus on making as fast of a race car as they can.
I think it's worth noting, most of us that have been here will have been on the team for 5 years. Most people come in as a freshman, don't know a lot, don't even know anything most of the time. Learn the machine, kind of find out what you're interested in. Your second year, you may be in charge of a fabrication group, so it's either composites, the CNC group, or the fabrication group. Third and fourth year, if you're devoted enough, you end up designing something. And then your fifth year, you may design something, you may take a break, you may be some sort of management. So it's a pretty long journey for most of us, and by the time we're in fifth year, I think we're all a little worn out, but we've all learned a lot, and it really is amazing how much you learn compared to class. We've all been here 5 years, but I can honestly say I've gotten probably more out of the formula team than school because it's allowed me to apply everything. It's allowed me to get co-ops that I definitely would have never gotten without it. Really opens up a lot of doors. So.
Are you able to do anything about fuel, like additives, standard fuel? Do you choose the fuel?
There's basically 3 fuels we're allowed to run a competition. It is sort of open, you can request more, but basically people are just running pump gas, 100 octane or E85. We don't really do any additives, we can't have any nitrous oxide systems or anything like that. And the fuel event has, in the past years, gotten more importance in terms of points. There's only 1,000 points in competition, and it's steadily increasing of how many points it's worth. So that was another thing that drives a single-cylinder engine. It's a little more efficient, you got less moving parts, so you're wasting less energy. And it's also a little smaller. We moved from a 600cc 4-cylinder down to that 450, so we're able to save some fuel that way.
Is there a question over here? Nando?
What pressures are you running for boost?
You can direct that question to Phil.
Right now, we're not running too much. We're pretty conservative, so it's around 4 to 5 PS. With more tuning time, we'll be able to get some more out of it.
The neat thing with turbo is it basically lets us pick what we want the power curve to look like, and it's pretty rewarding to watch Phil do a dyno pole, and instead of the typical pole we would have had in the past where it climbs, you make more and more power, and then at some point it drops off. It's kind of just like up and over, and then stops. Makes the car ridiculously easy to drive. It's just got torque all over the place. So.
That was my question.
We're getting there. Turbo's definitely been a learning process.
Who are your drivers and what do they weigh?
Well, this year...
Blaney never tells, so... At competition, we do have multiple events, but you can only drive 2 events per driver, so obviously we can't just have 2 guys that drive everything. Tim and Kevin are driving autocross and endurance this year. Kevin's a little more on the light side. But weight is important, not necessarily the most important thing for endurance and autocross, but especially for Excel, which is where Phil comes into play. I think Phil weighs like 100 pounds wet, so. And then on the other hand, I mean, me and Kyle drive skid pad. We're both pretty big dudes. have to reason the car is the shape it is, so I fit in it, which is what drove me to the chassis. So weight is important, but a lot of it does come down to skill and just the determination. Pretty tricky sometimes to find people who want to stay up till 3 in the morning to get the car running and then show up at 6 in the morning to drive all day out in the sun and only to have the car break and repeat about 7 times. So, and we have had some drivers in the past that were huskier dudes that were still pretty quick. So it's important, but it's not everything. Only they were here. Got any other questions, or everybody getting hungry? Yeah.
With your ground flex, how much force do you generate downward force?
With just the under tray?
Yeah, I heard that in a deal with force.
Okay, yeah, Kevin's probably the best. He's our lead aerodynamicist, so he spent all the time on that.
Whole package altogether produces about 400 pounds of downforce at 60 miles an hour.
And what's the car weigh?
335. 335. It's almost ready for competition. We got a few things to add, a few things to take off. So our weight goal is 330 pounds.
So you could drive it upside down remotely without a driver, right?
Theoretically. Yeah, we don't have a little more margin to pull it out. We'd have to maybe do that with Phil.
So with that force in the turn, can you pull a G or more than a G?
Yeah, 2.5. 2.5. Yeah. We have some pretty awesome tires we've switched to in the last few years, and we love them. They're pretty fantastic.
That's kind of the driving goal behind all this decision that we make. We need to have high lateral capability.
Yeah. And the whole idea of the car basically is that we reach the speed and we just stay there. It was a pretty big eye-opening moment for us. We went to Austria for a competition there 2 years ago, and one of our big competitive teams, GFR, it's a collaboration between 2 other schools. We had a car that made a ton of power all over the place, and basically we could pull away from them in the straights and they'd come into a corner and they wouldn't even slow down. They'd just shoot through the corner and keep going. And by the time we got back from that trip and after chasing them for 2 competitions, we came back, sat down, had a little talk, and thought we might want to do some simulation and see if we could be fast that way. And it's proven to be really successful. So it's kind of a hot direction people are moving in right now. A lot of teams are moving to smaller wheels and tires, single-cylinder engines. A lot of teams are running aerodynamic packages. So times are changing. People are finding out what's fast. People used to say wings don't work.
Tire warmers?
What's that?
Tire warmers?
No. You can use additives, but not at the track.
So if there's no final questions, and if you have any other questions, feel free to talk to anyone, any of us at any time. But we've cooked some hot dogs and hamburgers for lunch, so feel free to stop by, look at the car, get a closer look, talk to team members. We have the shop open up. You can take a look at all the things that we've been working on over the years, or over the past year. The team room's open. So basically open house, ask any questions.
And for any of the alumni that are here, we want to do a mock design event, probably last 45 minutes and a little bit. So if you guys are going to be around, that'd be awesome. We're all a little sleepy, but we need some practice. So thanks everybody for showing up.